Hi, welcome to this recording of our CG1112 tutorial 3. Okay, so in this tutorial, we are going to be recapping whatever we did for the studios. Okay, and making sure that we have a good understanding of the PWM and the timer module. Okay, now first let's recap the studio. Okay, what we have done for this week. In this week's studio, we were introduced to this DRV 8833 dual H-bridge motor driver. Okay, so this H-bridge, you are actually have been exposed to it before, okay, in your EPP1. Okay, so a H-bridge, as you can see, basically allows current to flow either in one direction or the other direction, depending on which combination of switches are open and closed. Okay, this is basically, as you can see, it looks like a H, so that's why we call it the H-bridge. Okay, and this H-bridge is actually the core of how this motor driver works. Okay, and basically the reason why we use two GPIO pins tied to A in 1 and A in 2. Okay, so this A in 1 and A in 2 are basically acting as switches to decide which combination of the H-bridge is on and off to allow the motor to spin one way or the other way. Okay, so that is the reason why we have the H-bridge. And of course, since we want to have a higher voltage and current supplied to the motors, we use the external power, okay, that is driving this chip. And once you get the project kit, you will be able to use the battery pack, okay, for this motor power. But in the lab, we use the DC power supply. Okay, so let's just look back at the code. Okay, so if you look back at what you did, you have the right motor forward and right motor reverse. Okay, and what we're going to do now is just to look back and see what we did. Okay, so when I was calling this function right motor forward, you can see that the first two bits here are 1 0, the next two bits are 0 0. Okay, so when I say it's 1 0, it is basically configuring the PWM mode. Okay, and when it's 0 0, okay, it is normal port operation and the OCO is disconnected. Okay, so when I'm doing it this way, so this is one channel and this is another channel. Okay, and this setting will make this channel have a PWM signal. Okay, and this one will be grounded. Okay, so that will allow the current to flow in, let's say, one direction. And in the reverse, you can see that the first timer's output is grounded. Okay, and this one has a PWM signal here, so the current will now flow in the opposite direction. Okay, so that is basically how we are using these two functions to make the motor spin in one direction and then in the reverse direction. Okay, so that is what we did in the studio. And another thing that I also mentioned in the studio is, how do we know the pins that OCOA and OCOB are mapped to? Okay, and this is actually available, okay, in the pinout diagram. So you can see that OCOA and OCOB are tied to port D, pin 5 and pin 6. Okay, so that is why in the code, okay, even though we never explicitly configure or look at why we use these pins, this is actually a reason. Okay, so whenever I use timer 0 and I want to generate the PWM, then I need to make sure I use these two pins as the output. Okay, so all the peripherals, okay, are multiplexed, okay, with the pins that we have on the controller. So whenever we want to use any of these features, we need to make sure we use the correct pins. Okay, looking back at how they are multiplexed. Okay, now let's go through our questions. Okay, so the first question is understanding the PWM module. Okay, so we saw that the 8328P has 3 timers, okay, capable of generating 6 individual PWM signals. Now consider the following scenarios and describe how you will be able to resolve the challenges. Describe a software approach to generate a PWM signal that is not dependent on the hardware PWM peripheral block within the microcontroller. Okay, so what are we asking here? Okay, so basically we are saying that if I have within the microcontroller, okay, if I do have a PWM or a timer block, okay, I can use that block to generate my PWM signal. Okay, but what if I do not have this? Okay, what if I do not have a PWM block? I do not have a timer block, a very, very basic, very low-end microcontroller. How can I still generate a PWM signal? Okay, and the way we can do it is in a software approach, we just keep on toggling a GPIO pin on and off, okay, for the required duty cycle. So this is basically how the pseudocode will look like. So if I take a normal GPIO pin, okay, so I take a normal GPIO pin, and what I do is I configure this as an output pin, and then I say let it go high, okay, and then I call a delay routine for T on, and then I set as 0, and then I call another delay routine, okay, for the T off. So this is the on time and this is the off time. Okay, and after that what I do, I repeat the code indefinitely, so I keep on generating this PWM. Of course, if T on and T off are the same, then you have a 50% duty cycle. Okay, if you want any other duty cycle, you just vary the T on and T off timing. Okay, so this is of course a software driven PWM, which is not so ideal. Okay, because if you use a software approach, then you are basically stuck in that loop to generate the PWM and not doing much other things that can be more meaningful. Okay, so definitely, as long as you have the hardware peripheral block, you want to make use of that hardware block to generate the PWM signal. Okay, so that is what is explained here. Okay, if I use the software approach, I am basically continuously executing this code, okay, and I am not able to do anything else. Okay, but if I have interrupts, okay, that helps me to ensure that these things happen, or these interrupts happen concurrently while I'm doing other things in the main program. Okay, and of course another thing is of course the timing characteristics. Okay, the timing characteristics are also very much dependent on the loop. Okay, so of course if I go back here, okay, you can see that if this is the only thing I do in my loop, then it is quite consistent. But if there are other things that I need to do, okay, be after I generate the two signal, then of course all this will play a part in the actual delay before I can do the on and off again. Okay, so it is not a very ideal approach to do the software PWM, okay, unless you really have no choice. Okay, so the next is question is basically telling you that you want to use a microcontroller that doesn't have any PWM module like what we saw just now, but I still want a PWM signal, okay, but I do not want to use a software based approach, okay, that you did in part 8. Now how can I do it? So this again is to recap some of the things that you actually learned in EPP1, okay, and basically what you can do is, one possible approach is to use the 555 timer to generate the required PWM signal. Okay, so in our EPP1 we have used this timer before, and I will not go into the details of how the whole timer works and how we configure it, because you have sort of done that before in EPP1. What I'm going to just look at is this output waveform. So you can see that I can actually generate a PWM signal, and of course T1 and T2 are very much dependent on the charging and discharging time, okay, which I can configure with the appropriate values for the RA, RB and C1. Okay, so that is basically one way in which I can generate a PWM signal that is not dependent on the microcontroller. Okay, of course one of the things here is adding an additional 555 timer and all those components is money, correct? So it's going to cost it's going to add some additional cost to your project, and you say, okay, never mind, I will just stick with the 8328P. Okay, and now I saying that you want a very low frequency PWM signal, and even with the largest prescaler setting, the period is too high. How will you able to generate a PWM signal with the required period? Okay, so provide at least two different approaches. So if you recall, basically our Arduino Uno, okay, Arduino Uno is clocked by a external crystal which is running at 16 megahertz. Okay, and now internally when I use it for the timer, I can actually use prescalers. Okay, so we saw in the studio that I can configure my registers to use prescalers to lower down the frequency, okay, to a much slower rate. Okay, but now the issue is even with the largest prescaler, it is still too high. You want it to be even slower. Okay, how can I still do it? Okay, one way is you can keep a track of how many times I actually jump into the ISR, and then use that count to toggle the pin to generate the required PWM. Okay, so this is an idea of how we can do it. Okay, so as you can see, whenever I generate the interrupt right now, okay, in the studio, what you saw is whenever the interrupt is generated, automatically I will toggle the output pin. Okay, so that automatic toggling, we need to switch it off. Okay, but we still enable the ISR. So what happens is inside the ISR, I keep track of how many times this interrupt has happened. So that allows me to to handle a much higher delay. And then when the required delay is achieved, then I can go and toggle a output pin to 1 and then wait much longer and then decide again. Okay, so this time can now be very, very long because I can count the number of times this delay has happened. Okay, number of times the delay has happened. So this is one way in which you can do it. Okay, so of course if I want to do this approach for my ATmega 328, I need to make sure that the automatic toggling of the output pin is disabled, and then I just directly control the GPIO pin inside my ISR. Okay, so I keep track, okay, the number of times the ISR has been triggered, and then I use that as a number to decide when to toggle the output pin. In our AT328, we also have another option, which is the 16-bit timer. Okay, timer 1. So we have a total of 3 timers, 0, 1, and 2. And in timer 1, we actually have a 16-bit timer counter. Okay, so you can actually count to a much higher number, which can give you the required delay. Okay. Okay, in question 2, we are trying to look at the situation where you have 2 motors running concurrently. Okay, so in the studio, you are driving a single motor. Okay, but now we are saying that we have 2 motors and we are using both timer 0 and timer 2. Okay, and both the timers are configured to use interrupts. Okay, so let's understand what would happen if both of them, okay, were to request for interrupts at the same time. Okay, so if both of them request for interrupt at the same time, what would happen? What would be the sequence of execution? So you can see here that from the main, okay, so when the main is running, okay, at some point of time, okay, at some point of time, you have a timer 2 generating an interrupt request, and at the same time, you have a timer 0 generating interrupt request. And you can see that I am jumping to timer 2 first. Okay, why is that so? Because for interrupts, there is a concept of priority. Okay, so all the interrupts that can trigger the microcontroller have a priority, and when interrupts are happening concurrently, the controller will always switch to the highest priority first. Okay, when interrupt is triggered. Okay, now as you can see, what would happen is at this point of time, I would stop whatever I was doing, save a snapshot of it, and jump over to my timer 2 ISR. Okay, so that is this context switch. Okay, so the context switch is basically telling us that we are making a snapshot of wherever we were in the main, okay, and saving that context and switching over to the ISR. I will complete the ISR and I will come back. Okay, so that coming back is another context switch because I want to revert back to how I was. Okay, but when I switch back, the controller will see that there is actually another interrupt that I need to service, which is the timer 0. Okay, so there will be again a context switch to the timer 0 ISR. Okay, and in that ISR, I will complete the ISR. Okay, and then I will return. Okay, so this is the context switch to the timer 0, and then from the timer 0 ISR, I will return, and then only I'm able to carry on with the main program. Okay, so this is basically what would happen if both the devices, both the peripherals had requested for interrupt at the same time. Okay. Now, what if timer 0 triggered the interrupt just before timer 2? Okay, so if I were to draw the timeline, okay, this is T. So I say at this point of time, okay, timer 0 triggers. And maybe just after that, very little time after that, timer 2 triggers for interrupt. So both of them are the interrupt request lines. Okay, now what would happen? Okay, if timer 0 happened to come in first, okay, then I will jump to timer 0 first. Okay, then do the context switch and then come to timer 2. So even though timer 2 is higher priority, but if timer 0 came in first, then I would service timer 0 first and then come back and switch over to timer 2. Okay, so that is the default behavior of how the ATmega behaves. Okay, why? Because by default, this concept of nested interrupts are disabled. Okay, so what are nested interrupts? Nested interrupts means within an interrupt, I can get interrupted again. Okay, so by default, nested interrupts are disabled. Okay, so in that situation, when what happens is when I jump to ISR, okay, the nested interrupts being disabled, I will carry on with the ISR first, finish the ISR, go back to the main, and then service the second interrupt. Okay, so when the second interrupt triggers, it is actually captured by a flag. Okay, the flag is set to tell the controller that there is this pending interrupt. Okay, but I need to wait for the current ISR to complete before I can context switch to the main and then switch back to the ISR that is still pending. Okay, now what if nested interrupts were enabled? If nested interrupts were enabled, then this is what would happen. Okay, so I would be in my main. Okay, and then at some point of time, timer 0 generates an interrupt request, so I will jump to timer 0 ISR. So I'll do the context switch I'll be doing, but before I finish, there's another request here for timer 2 interrupt. Okay, so that would cause me to jump to timer 2 ISR, finish everything, return back to timer 0 ISR, finish this ISR, then go back to main. Okay, so that is how the behavior would be like. Okay, so this again is only possible if nested interrupts are enabled. Okay, by default, the ATmega does not enable it, so by default it is disabled. Okay, so but of course if you enable it, a higher priority interrupt can preempt a lower priority interrupt. Okay, so that is what we are trying to show you here. Now let's go on to part 2. Okay, so in part 2 we are going to be looking at the timers and interrupts. So again, quite related. So the first question here is on the 328 data sheet about the timer interrupts, okay, and fixed intervals. Okay, now first thing is what are two examples of users for the timers? Okay, so one example here is to configure a periodic timer that will come every 1 second and then write a soft real-time clock. Okay, what is meant by a soft real-time clock? A real-time clock, as we know, is to keep track of the actual time. That means your seconds, your minutes, your hours. Okay, and of course you can extend it to the actual calendar itself, the days, months, and years. So this link, Prof Colin Tan has written, okay, a code, okay, for this software-based real-time clock. You can go in and have a look. Okay, and of course if you want to use it for any application, you're free to use it since it's open source. Okay, another example of timers is used in operating systems, okay, where I want to continuously switch between tasks. Okay, so for example, your mobile phone, all your computer devices, all majority of them that are highly complex use some operating system. And in operating system, you are actually having multiple tasks, okay, that are running in the environment. Okay, so timers are used to keep track of how much time each task is actually consuming. Okay, of course, we're not going to go into details here. You will learn more on operating systems in 2271. Okay, when you take it in your year 2 module. Okay, this question saying that timer 0 and timer 2 are 8-bit timers. What does the term 8-bit timer mean? Okay, in terms of interrupt triggering intervals. Okay, so if my timer is 8-bit, okay, that means I can count from 0 to 255, correct? Which means that the highest count is 0 to 255, and of course, as we saw earlier, I can choose to slow down the time it takes to count from 0 to 255 by using a prescaler, okay? And the largest prescaler I can have for this timer 0 and timer 2 is 1024, okay? So since the Arduino that I'm using in the lab is running at 16 megahertz, if I take that frequency divided by 1024, this is the frequency or the lowest frequency at which I can clock my TCNT0, okay? Uh, so this turns out to 0.000064 seconds between increments. That means when my counter is 0, the longest interval I can have before I go to 1 is this, okay? 0.000064 seconds, okay? So that means counting, okay, from 0 to 255 will take me around 0.01632 seconds. So this is the longest time I can take. The longest time I can take to count from 0 all the way to 255, okay, for timer 0 and timer 2, which are running on 8 bits, okay? Now, timer 1 has a 16-bit timer, okay? So what is the use of the 16-bit timer? Since it's 16-bit timer, I can count from 0 to 65535, correct? So with the same clock, okay, as just now, and the same prescale values, okay, I can say that the amount of time that I take to count from 0 all the way to 65535 will be 4.1924 seconds. So you can see that I can have a much larger interval, okay, for the full duration of the timer going from the smallest to the largest value, okay? So that is one of the advantages of having a timer with more bits, okay? Of course, what is the disadvantage is, since the 16-bit timer, most of the registers that we deal with it are also 16-bit, okay? And since the 328P is an 8-bit microcontroller, it takes you can set registers one at a time or 8 bits at a time. So the setting up also may take a bit longer, okay? And of course, it take up more space on the chip as well. Okay, in timer question 2, we are basically looking at the CTC mode, okay? So this CTC mode is another mode of operation that your timer can operate in. So we saw the PWM in class. Okay, so in CTC, basically this picture here shows you how it behaves. The TCNTN register counts up all the way, okay, till it has a match with the OCR register. And once it has a match, it will reset back to 0. And at that time, you can decide to generate some interrupt, okay, or in this case, you can decide to toggle the output pin, okay. So that is how the CTC mode works. Now we are given that the TCCR 1A and 1B registers are configured with these values. So what does this actually mean? What do these setting of bits mean? So this is actually an important skill set that you must develop, okay, as a computer engineer, because in most cases the information that you want is inside the data sheet. So you must make it a habit to be able to look at these data sheets to extract out the information that you want, okay? So if you go back to the data sheet and look at the section on timer 1, okay, and see these registers, okay, you'll be able to get their meanings, okay? So very similar to what we did for timer 0. So the first 2 bits here is referring to the behavior for the compare match, okay? So 01 means both A and B will toggle whenever you have a compare match. Compare match is when the TCNT register has a match with the OCR1A register, okay? So when that happens, you will toggle the output, okay? Now of course the waveform generation bits here is to basically configure the mode of operation to be CTC, Okay, so you can look back at the data sheet for timer 1, okay, and see how these bits are configured. So in this case, this waveform generation bits are 4 bits long, okay, and these 4 bits have a different combination depending on whether you want to operate in phase correct PWM, fast PWM, and CDC mode. Okay, so you can look at that table in the data sheet to have a better idea of how this works. Okay, and of course the last 3 bits of the TCCR1B is the same as timer 2, timer 0 in the class, which is the prescaler. Okay, so in this case 100 refers to a prescale value of 256. Okay, now what is the interval between which timer 1 compare A vector A is triggered? Okay, so this is basically the interrupt, correct? The interrupt service routine. So what is the interval between when the interrupt is triggered? So since we know that the prescale value is 256 and the main clock is running at 16 megahertz, okay, so that gives us a period of 16 microseconds. Okay, and the period therefore is 247 plus 1. Okay, so this is again taken from the data sheet. Okay, and this 247 plus 1 is basically how we calculate the timing from the time when it takes from 0 all the way to the value here. Okay, so that is why it is 247 plus 1. 247 is the value inside the OCR1A register here. Okay, so whenever the TCNT register counts, okay, so from 0, 1, 2, it will count all the way to 247, and then it will trigger the interrupt, okay, and reset back and count again. Okay, so that is how the timer module for timer 1 here works in CDC mode. Okay, and how will the waveform look like? Okay, so since I'm operating in toggle mode, okay, you can see that every 4 milliseconds, or around approximately every 4 milliseconds, you will toggle the output. So the waveform will be approximately having a period of 8 milliseconds. Okay, so that is how the this waveform works. So you can see that this CDC mode, in a sense, can also be used to generate a PWM signal. Okay, generally it is easy if your PWM is a 50% duty cycle, because if I decide to toggle on match, then it will always have the same starting point. So I'll always go up to the same starting point and reset, same starting point and reset, correct? So every time it will toggle. So here it could be a 1, then here will be a 0, and so on. Okay, so I can easily generate a 50% PWM, okay, in toggle mode. Okay, of course, if I want other duty cycles, then it's a bit more complicated, because then I need to think of what is the OCR value that I want. Okay, so if I want PWM, okay, with a high and a low, then for this I have a separate OCR value, and for this I have another OCR value. So I have OCR1 and OCR2. I mean the same register, but I need to update it with 2 separate values, because I will now need to count different timing intervals. So it's a bit more complicated if I want to use the CDC mode, okay, for PWM generation. So it is not advisable. So that is why we can directly use the PWM mode of operation, okay, to generate the required signal that we want. Okay, whereas over here we use it, okay, to count and generate periodic interrupts, okay, for us. Okay, in this last question, we are basically trying to understand the effect of a rounding error, okay, when we are configuring the prescale value. Okay, so what I want is, I want a timer 0 in CDC mode to have a interrupt, okay, every 650 microseconds. So this is again one of the ways in which you use CDC mode, where you want periodic timing interrupts. Okay, if I want PWM, I operate in PWM mode, but when I want periodic timer interrupts, okay, even without toggling the output, I can still use the ISR to do other things that are important. So this 650 microseconds periodic interrupt, what I'm doing here is I'm trying to see how the rounding error actually works. Okay, and what I have is the clock running at 20 megahertz. Okay, so this is a bit higher. The board we have in our lab is running at 16 megahertz, but if you look at the data sheet, the maximum I can clock it at is 20 megahertz. Okay, so if I'm clocking it at 20 megahertz, then the prescaler value, after I go through the prescaler, the period will be P over 20 meg. Okay, so if I have a prescaler of 64, that means after I divide this 20 megahertz by 64, I get a period of 3.2 microseconds. Okay, so that is the period at which I will increment the timer value. So if I want to achieve 650 microseconds, then I'll take 650 divided by 3.2 to get a count of 203.125. Okay, so of course I cannot put this into my TCNT register. It's I can only put a fixed integer value, so I will put a value of 204. Okay, why? Because the question just now said you round up. Okay, so I'll round up to 204. So if I round up to 204 and I work backwards now, okay, which means that 204 times 3.2, I will get a periodic interrupt every 652.8. Okay, so you have to remember that the CDC mode, basically I count from 0 all the way until I have a match. So TCNT must match the OCR register. Okay, so the OCR register must have a value. Okay, so in this case, that value is 204, and the timing interval, okay, so for me to go 0 to 1 to 2, that timing interval is 3.2 microsecond, okay, based on the clock frequency of 20 megahertz and a prescaler of 64. Okay, so that is what we are trying to do here. Okay, the timer is slowly incrementing up to the point where it matches the OCR value. Okay, so in this case, the OCR value is 204. Okay, so with each timing interval taking 3.2 microseconds, I will have a periodic interval every 652.8 microseconds. Okay, so what I wanted was 650. Okay, and what I got is 652.8. So there is a slight error here. Okay, so the error is 0.43%. Okay, now of course you are supposed to repeat the procedure across all the prescaler values. Okay, so if you do that, you will get this table filled up. Okay, and basically what we are doing is, here you can see all the prescale values. Okay, 1 all the way to 1024. Okay, and based on the prescale values, what is the period here? Okay, so again, this is with reference to the clock frequency of 20 megahertz. Okay, now for prescaler of 1 and 8, you can't really fulfill it. Okay, because you won't be able to achieve the timing that you want. Okay, so we are only looking at 64, 256 and 1024. So for these three options, you see that 64 and 256 give you the same actual period. That means the error is the same, whereas when I divide by 1024, it is much larger. Okay, the error is much larger. Okay, and why is this so? Because the higher the prescaler means, the larger the difference in timing, correct, between one count and another count. Okay, so imagine that right now, okay, if my pulses are very close together and this is what I want, then the error between this and this edge is very little. Okay, whereas if my timing is something like that, okay, then based on the interval that I want and where the edge will come, the clock edge will come, is going to be a lot bigger, correct? So generally with larger prescalers, you can have a bigger error, okay, when you want the specific timing that you want. Okay, of course in some cases there may be no error if it's a very nice multiple, okay, of the period and the timing that you actually want. Okay, but in this case you can see that the error can be quite large. Okay, so that is why generally a smaller prescaler is good, okay, to reduce the rounding error. Okay, so again, this is a good point to note. Okay, because even though the error just now when we calculated, okay, if you go back here, the error is very small, 0.43%, but in some situations you have to remember that if your controller is running indefinitely, okay, this 0.43% will add up. Okay, so there can be a cumulative error that builds up that will eventually cause a larger delay. Okay, and of course in some cases maybe it is not significant. Okay, I mean, if you imagine you have a digital watch, okay, and every 1 month it goes off by a few minutes, then you may just readjust back. Okay, but in other cases, maybe those few seconds or even few minutes of drift, okay, over time can be serious. Okay, so as much as possible we want to avoid this kind of errors, or maybe think of how we can compensate for it at a periodic basis. Okay, so that sort of wraps up the tutorial. Okay, so this set of slides, these additional questions on serialization, we will not go through, okay, because is quite a lot of new material, which I think you will better understand after you go through the next week's e-lecture. Okay, so during our actual studio, I will explain these questions and the UART protocol and how it works in more detail. Okay, so thank you for watching this e-tutorial. Again, if you have any doubts, anything you're not sure after watching this video, no issues, you can consult me, okay, anytime, okay, or if not, we can also have a discussion for all your doubts during the studio session. Okay, thank you. I'll see you all in class.